Alright. So next operation is the read operation. So now you want to read the data out. Let's assume that in this case, N1 stores 0, N2 stores 1. As we discussed, we always think that the data read out from the bit line will be the data you stored. So in this case, we store 0 in this SRAM cell. So how do we read the data out? Read data out means that you need to read the data out through the bit line, because bit line will connect to the outside of the array through your colon decoder, colon marks to the outside of the array. So you want to read the data out. So how do you read the data out? So here you need to apply a few steps. First means that is that for bitline bar, you need to pre-charge to VDD. Pre-charge to VDD, what does this mean? Okay. So we need to treat the bitline bar as a capacitor. So we have this wire capacitance for the bitline. Why is that? The bitline, is a metal wire. It's an interconnect. And we learned in the lecture 2, you have multiple bit lines, you have multiple wires. Between wires, you have isolation. So it's like a metal wire, isolation, metal wire. So this is like a cap. So you have the parasitic capacitance of the bit line. So the bit line actually is more like a capacitor, and with a wire capacitance CW here, or CDL. So we need to pre-charge this cap of this bit line to be VDD, and also the bit line bar to be VDD. And then we turn on the word line. So here the word line will be turned on. That means you apply VDD to the word line. So after you apply VDD to the word line, let's look at the circuit here. So this is pre-charged to VDD, and then the gate of your PG1 is also VDD. And here you store 0 to the N1. If you look at this transistor, this is NMOS. Your VGS, this is G, this is D, this is S. So your VGS is VDD, and the VDS is also VDD. So this transistor is turned on and it's in the saturation. So you will have current flow in this way. So this current must sink to the ground. So this current will go through the PD1 to the ground. So you see this green arrow. This is a current flow in this case. So if you have current flow from the bit line to the ground, bit line is like a cap. That means you are going to discharge this cap. That means initially, if the voltage is VDD, and over time, this voltage will decay. So if you look at the waveform here, initially, the bit line is VDD, the red line. And then, once you turn on the word line, then this discharge current, this green arrow, will discharge the bit line. So you will have a decay of the bit line voltage. And then the bit line voltage initially is VDD. Now it will become VDD minus this delta V, which is a decay of the bit line voltage. So this is on the left-hand side, this N1 node. How about the N2 node here? So N2 node stores 1, that means the voltage is VDD. And the pass gate 2, the voltage is also VDD to the gate. And the bitline bar is also VDD. So for the pass gate 2, PG2, you see that the bitline bar will have no change, because here 3 terminals have the same potential, then no current flow through the PG2. That means the bitline bar will stay at VDD. So here you see the waveform, the blue line, stay at VDD. So here stay at VDD. I got one question. So on the red line, the VDD will discharge. Red line, yes. Here, this is to the bit line. The bit line will discharge because the current flow from the PG1 to the PD1 and to the ground. So the bitline voltage will decay, will change, but the bitline bar will stay. Okay, so you see the difference in the voltage. And what you will do here is outside the memory array, we have this so-called sense amplifier. It's an amplifier to detect the voltage difference between those two. So this bitline bar will be sent into an amplifier. So here, amplifier, differential amplifier. You may have seen the op amp in your 2040. So it's an amplifier. You can detect the difference, right? So this one is smaller than the bitline bar. So this sense amplifier will detect the difference, and the output will tell you this is 0, this side is 1. So we are not going to discuss the sense amp design in this class, but the amplifier can amplify the small signal difference. So here the bitline is smaller than the bitline bar, then the output will tell you that this bitline is 0 and bitline bar will be 1. So this is how you read the data out. You see your data stored in the SRAM cell, but you can read it out to the external circuits through this sense amplifier. So the key is that you develop the voltage difference between the bitline and bitline bar. So the key is that you have the discharge current to the bitline through the PG1 and PD1. Any questions? If no, then let's look at the PG1 and PD1 in more details. I got another question. Why are you recharging bitline? Why don't you just activate the pass gates and read off the bitlines? So here we need to pre-charge the bitline because we want to look at that delta V, that voltage decay, right? You need to pre-charge both bitline and bitline bar to be VDD, and then one side will decay, the other side will stay. So we can have the difference between the voltages, so we can sense. Theoretically, you can pre-charge them to be any level, and then as long as bitline and bitline bar have the same level to start with, and then you will see the voltage difference. But if you pre-charge to be VDD, then the delta V, the margin will be the largest when you have the decay of the voltage due to the discharging. So that's why we do it both bitline and bitline bar pre-charge to be VDD. So basically, you need to have the same starting point, and one side you have the current flow, the other side you don't have current flow. So you will develop the voltage difference between those two sides. So this is a key. Okay, let's look at this. Here, this is the current flow from the PG1 and the PD1. Actually, here only those two transistors are active in this read operation. The other transistors are off. There's no current flowing in the other transistors. You can verify that by yourself. So only those two transistors are working here. So let's analyze those two transistors in details. So this PG1 and PD1, and then here this is N1 node. And initially you store to 0 here. But you have the VDD here, and then you have the current flow this way. So you can think the PG1 and PD1, if we approximate the transistor as a resistor, you can think them as two resistors to form this kind of voltage divider. So this is your PG1, and this is your PD1. So initially this is VDD. So initially this node is your N1 node is 0. But since you have current flow here, this node cannot be 0 because it's voltage divider, right? So this 0 will increase to some voltage. Let's say V prime. So here the thing that we want this voltage increase to be as small as possible. Because after you are done with the read, you want the N1 node go back to 0. Because when you read out the data, you don't want to change the data. So you want this N1 returns to 0 after the read operation. That means here when you do the read operation, the N1 cannot increase too much. How can we get another question? How can we know that N1 store value is initially 0? Okay, this is our assumption, right? So in this example, you only have two stable points. One is N1 is 0, N2 is 1, or you have N1 is 1, N2 is 0. You only have those two stable points in this circuit, right? This is a latch. And in this example, we assume N1 is 0. Of course, you can have the other case, then we have to analyze the N2 because N2 will be 0 in that case. But everything will be symmetric, so it basically is the same. So let's just assume that N1 is 0. Okay, so this we want this N1 to be close to 0 as possible during this operation. So this is a voltage divider. How do you ensure that? This is voltage divider. That means the resistance of this PD1 should be small. Let's say smaller than the resistance of PG1. Right, this is the voltage divider, and you know the this V prime is the voltage division between the, let's say, RPD1 plus RPG1 over RPD1. So and times VDD. So you want this one close to 0. Then you want the PD1 to be small. Then this N1 is close to 0. So the resistance to be small. Of course, if you think they are resistor, but actually they are transistor. Okay, transistor, how do you determine their channel conductance? It depends on the W over L ratio, right? So in other words, if you think about conductance, then the PD1 will be larger than PD2. Oh, sorry, PG1. Because resistance and conductance, is inversely proportional. And the conductance is determined by this mu COX W over L ratio. This conductance is how much current you can flow. Then it depends on this. So both this PG and PD transistors are NMOS. That means mu N COX are the same. So only what matters here is the W over L ratio. So if you want to do this, then you want the W over L of the PD larger than W over L of the PG. If we define this ratio, is this one divided by this one, that means this beta larger than 1. Or in other words, you want the pull down to be stronger than the pass gate to be weak. If you want to satisfy this condition, this N1 is close to 0. We can understand this better by looking at this timing diagram in the operation. For the read, as we discussed, you need to prepare here the bit-line bar both to be VDD to start with, and then you turn on the VLAN. Once you turn on the VLAN, here we have this discharge current through the PG1 and PD1. So then the N1 node initially is 0. Now, because we have this current flow, this voltage is raised up a little bit to here. But you don't want this to be too much, okay? And then the bitline will decay. So we have this delta V here. once this delta V is large enough, we can sense it out. Then after we are done with the sensing, then we can turn off the word line. So after we turn off the word line, then we want this N1 go back to 0 because you don't want to change the data after you read. So similarly, as you know, this is like a voltage transfer curve for the inverter because in the middle, it's inverter. So N1 and N2 actually, if you look at the voltage for N1 and N2, is actually the VTC curve of the inverter. So this means during the read operation, you are introducing some noise into the N1 node. It's like the N1 is initially at 0, but during the read, you are changing the voltage to here. This vapor here, this vapor. And after the word line is closed, it's like you are going to restore this signal back. Due to the noise margin, the feature of the inverter, then this will go back to 0. So this is why we want this one to be small enough. If it's too large, then this will flip. So that's why we have this kind of requirements on the W/L ratio. I got another question. How much can this voltage rise? Will this rise up till noise margin? It's not exactly the same as the noise margin because there's this is a little bit more complicated. I don't want to discuss that in this class. What values you need to reach. But as long as you know that there's a limit in practice, like to 100 millivolts, 200 millivolts. But there's no simple analytical equations that you can derive this maximum voltage before you reach this flipping. So I don't want to go into this details of that. So as long as you know this one needs to be small. Okay, so this is I got another question. So what do N1 and N2 represent? N1 and N2 represent those two nodes, two storage nodes here. This inverter, these two nodes. And N1 and N2, here's the voltage. It's like a VTC, a voltage of N1 or voltage of N2. Oops. This is a voltage. It's the input and output of those two inverters. They are cross-coupled. Okay, one more thing is on the read speed. Okay, how fast can you read the data out? We can always use this kind of equation to look at the speed. We consider the current flow, that green arrow, that current. That current is going to discharge this bitline cap. So this current, and then you take some time. For example, if you look at the bitline voltage here, the voltage will decay over time, and we want to know how long we need to take before you reach the sense margin delta V, that is the decay of the voltage. And then the current multiplied by the delta T is the charge you get out of the bitline cap. And then this delta Q also equals to the bitline capacitance times the delta V. So you can get the delta T equals to this C bitline times this delta V divided by the I through the Q5 in this cascade, or let's say in practice is the PG current. And typically the bitline cap is like, let's say 100 femtofarad, and then the delta V, the small voltage you can sense, 100 millivolts. And then if your current is 1 microamp, so you can calculate the delay. So let's do it. So let's say this is 100 femto times 0.1 volts. So this gives you 10 femto divided by 1 micro will give you 10 nanosecond. But actually the current typically is like, let's say 10 micron. If you do that, then it will give you 1 nanosecond. So that's why the SRAM is fast. You look at this number. Your transistor can easily give you 10 micron. Transistor give you 10 micron, and then you discharge this 100 femtofarad cap, then you just need 1 nanosecond. So that's why the SRAM is used for the cache. So it's fast, 1 nanosecond. 1 gigahertz of your clock frequency means the clock cycle is 1 nanosecond. So this one can do the readout within 1 nanosecond. All right. So let me stop this one.